Okay, so this video refers to Lecture 4 moments, and specifically looking at analysis of moments, not about a point but about an axis. So if we think about some of the previous examples we've looked at, we've had structures, beams, frames that have had forces applied. We've looked at the moment acting about a point. If you look at slide 27, you've got a tyre, and if this is my tyre, use your imagination if you can't quite see it, but you've got your tool there removing the bolt. As you apply a force here, the force isn't acting just about this point, but it's acting all the way along this axis, that turning effect. So what we can now do is we can start scaling up. Rather than talking about moments about point, we're now looking at moments about an axis. The only difference is, if we call that point O, and this would be the y-axis in green. So the moment about point O would equal a cross between the r vector and the force being applied. The moment about the a-axis, apologies, that's not a vector, but the moment about the a-axis, the magnitude of that moment, would be my moment about O, and with a dot product with a unit vector for the a-axis in there. So we're going to have a cross product and a dot product together. It's not as hard as it sounds. Rather than talking through the actual examples more than that, rather than talking through the slides more than that, I'm going to go straight into an example. So if you turn to slide 30 if you're following the lecture notes, and I'll attempt to draw it, and then we'll see how to solve it. So clearly I haven't drawn that very well. You can follow it much better in the actual lecture notes. We've got point O, we've got a point A, we've got three angles that are meant to be your alpha, your beta and your gamma angles, and we've got two distances. So we can start to solve the moment, both the moment about the point O, but also how much that turning moment, that turning effect, is about the x-axis. Because if you imagine your x-axis is down here, how much of that turning effect that's being applied by your force is actually trying to pull the whole handle and turn it around the x-axis. So turn everything that way. It will be that way because it's lifting it, so that way about the x-axis. So we need three bits of information. Our unit vector for this question will just be 1i. Why is it 1i? Because it's the x-axis we're interested in, so it's only the I direction. Our r vector, our position vector, will be 0i, because there's no displacement in the I direction. We've only got 0.3 in the y direction, so 0.3j, and we've got 0.25k. And our force is going to equal 200, and then it's the alpha, beta and gamma angles, so we can say cosine 120i plus cosine 60j plus cosine 45k. And if you're not sure why they're alpha, beta and gamma angles, if you refer to the earlier videos, but basically it's because this angle here is going all the way from the force straight to the x-axis. This angle here is straight to the z-axis. This angle here is straight to the y-axis from our force. So that's going to equal minus 100i plus 100j plus 141.4k. And now we can start to place those numbers into a matrix. So you're going to need the three Cartesian vectors. I'm just going to jump to a new page. So our matrix for the moments, it was the moments about the x-axis, I think. Yeah, so moments about the x-axis. 1, 0, 0, no longer I, j and k. 1, 0, 0, that's your unit vector that you're substituting in there. And we only had an I component. 0, 0.3, 0.25, so that's your R vector as before. Minus 100, 100, 141.4. We're going to do exactly what we did before. So we're going to do, to start with, 0.3 times 141.4 minus 0.25 times 100. I'm going to times it by 1. Not by I, by 1. I'm then going to do 0 times 141.4 minus 0.25 by minus 100. That would all be negative because it's your j component, your second component. And I'm going to times it by 0, which is obviously going to be 0. I see a pattern developing here. A final component, I'm going to do 0 times 100 minus 0.3 times minus 100. I'm going to times that all by 0. That would originally have been a k in the previous examples we've been doing. So the only line that's got any numbers in it that's not times 0 is the top line, the green line. If I follow that through, my moment will then equal 17.4 Newton meters. There's no I, j and k component because there's no i's, j's and k's in the matrix anymore. So that is how you'd solve a moment question looking at the moment applied along an axis rather than about a point. There is a group problem solving question that starts on slide 34, looking at the hood of a car or the bonnet of a car. If you have a go at that, pause the video, have a go at that, and then come back to the video and I'll show you how to solve it. So you should have had a go at the group problem solving exercise from beginning on slide 34 of lecture 4. Again, if we work through in the same way, I'm not going to try and draw it because my drawing's not that good. You may have had to put 1 or 2 more steps in that you learnt from the previous lectures. But first of all, let's look at what we've got. Well, it's asking about the moment about the hinged y-axis. So we know that this time our unit vector is just going to be 1j. Our position vector, this is where it gets interesting, that's our unit vector we're interested in. Our position vector A to B, because A to B is the direction of the force. To get from A to B, you're going to go backwards 0.6 in the I direction, 0.6 meters. Forwards 0.6 in the j direction, and upwards 1.2 in the k direction. You don't have your force as a Cartesian vector, you just have its magnitude, and its magnitude was 120 newtons. So you're going to have to use your position vector A to B to get a unit vector A to B to then get a Cartesian vector for the force AB. So the magnitude of AB is going to be 0.6 squared plus 0.6 squared plus 1.2 squared, all square rooted, which is going to be 1.47 metres. So the length of that arm that's holding up the bonnet there is 1.47 metres. My unit vector A to B, which I only need to get the Cartesian force A to B, is then going to be minus 0.6 over 1.47 I plus 0.6 over 1.47 J plus 1.2 over 1.47 K. And then my force AB as a Cartesian vector is going to be 120 times minus 0.6 over 1.47 I plus 0.6 over 1.47 J plus 1.2 over 1.47 K. If I multiply that out, I'm going to get minus 49I plus 49J plus 98K. And now I can transfer those 3 bits of information, so my unit vector, my position vector, my force vector, this unit vector being for the axis around which you want the moment to be calculated. I can transfer those into a matrix. So my moments about y are going to be 0, 1, 0. It's only about the y-axis, so we've only got a 1 in our middle section of that top line. Position vector was 1.2, 0, 0. Where did that come from? That 1.2, I actually told you wrong on the previous slide, so we jump back a slide, where I said you'd need this position vector. The only reason that you do any of this all leads you to that, so that only gives you the third line of the matrix. So if we transfer that in, minus, whoops, sorry, stayed as green, minus 49, 49, 98. My moment is actually equal to my unit vector, i.e. 1j, dot product with ROA crossed with F. But we haven't got ROA, we've got RAB on the other slide. ROA, where does the force start from in relation to the origin? Well, the force related to the origin starts 1.2 metres away, so in the x direction. So ROA, which is what we actually want for our diagram, for our matrix, sorry, is 1.2I. That's saying I've got so I've got my axis along which I want the thing to start. I've got my Cartesian vector for my force, so which direction is the force actually acting in, and I've got my where's it starting from. So we're saying I've got this force, I've got a force acting in a direction from a starting point. What effect does it have turning it about an axis? I was reading the matrix upwards. Hopefully that makes sense. I'll say that one more time. I'll take these out and redraw them. So we've got a force acting in a direction. It's starting at a point relative to the origin, and we want to know what turning effect it has along an axis defined by this unit vector. So we'll do the cross product of the bottom 2 lines and then multiplying the top line. So we're going to get, let's clear some space. We're going to get only a solution with this bit, because the other 2 bits are going to be times 0. So it's going to be this times this, so 1.2 times 98. And we're going to have minus 0 times minus 49. and then it's all got to be times 1. Because it's the middle, what would have been our j component before, it's got to have a minus at the start. So it will come out at minus 117.6 Newton meters. Or you could say 117.6 Newton meters in the clockwise direction. So that's introduced the idea of moments acting about an axis rather than about a point, and solving them using vectors, using a combination of the cross product from the previous examples, but then adding in an extra step of the dot product with a unit vector that defines the axis of interest. And that refers to lecture 4.